Hello everyone, my name is Danielle Depierri, and this week I'm going to be doing my 6-minute talk on heat exchangers. My objectives for this presentation are to teach you what are heat exchangers in general, their basic working principles, and different types of heat exchangers, how those work, and how you can select what type of heat exchanger you want to use, and also a few common applications of them in industry. So for the overview, the main purpose of heat exchangers is to facilitate heat transfer between two fluids. This is performed usually by separating these two fluids because you don't want them to mix, and those can be separated by either a planar wall or commonly a cylindrical wall. And as you can see in this diagram here, there's an inlet and outlet for both your hot and cold fluids. This is an example of a tubular heat exchanger, but there's a lot of different types. And they can be used to either heat or cool a fluid, or sometimes do both simultaneously, depending on what you're trying to get out of it. Commonly though, it's often used for cooling in industry. As far as the working principles, it's really just heat transfer. There's a temperature gradient, that's the main governing principle behind it. Temperature or heat flows from high temperature to low temperature, and the heat transfer in heat exchangers is primarily convection between the two fluids. But like I mentioned earlier, there is that barrier, like a wall or a cylindrical wall. So conduction does occur across that point, but it's really negligible, and you want it to be negligible because that's the whole point of the heat exchanger, to get the maximum transfer between the two fluids and a minimum heat loss in that wall. As far as the governing equations behind heat exchangers, it really depends on what type you're looking at. There's a whole bunch of them. But for super simple configuration with no phase change and a constant specific heat, so like not for condensers or evaporators, this is the equation you can use, where Q is your heat rate, m dot's your mass flow rate, Cp is your specific heat, and then you have your two temperature changes for both your hot and cold fluids. As far as comparing heat exchangers to each other, there are heat exchanger efficiency equations. In heat transfer, we learned about the NTU method, but those are super extensive and complex, and again, depend on what type of heat exchanger you're looking at. But if you wanted to make like a general comparison just between two, you could calculate the overall heat transfer coefficient for the heat exchanger, as well as the total surface area that heat transfer is occurring across, to compare the performance of two heat exchangers. So in this equation, you use the log mean temperature difference. Like I mentioned earlier, you have two delta T's, one of your hot fluid and one of your cold, and this is kind of like an average of both of them, like an overall delta T for your entire heat exchanger. And these are two equations that you can use, one for shell and tube and one for plate and frame, across one tube and one plate, where you can calculate the overall heat transfer coefficient. Your RF here is, or all the R's are thermal resistance, like a thermal circuit, but RF represents your fouling resistance, and RW is your conductivity resistance. And conductivity is also represented in shell and tube. That's the natural log equation. Just looks different because it's cylindrical. And fouling is something that commonly occurs in all heat exchangers. It's kind of inevitable. It really just means that it's gotten dirty and needs to be cleaned. But it really depends on what fluid you're working with as far as how much fouling you're going to see, and also what type of heat exchanger you're looking at. So two common types I'm going to be talking about are shell and tube and plate and frame, like the equations I showed on the slide before. The image on the left is shell and tube. You can see all the little holes are actually little tubes, and on the inside of the pressure vessel is just like open air, and that's where one of your fluid goes, and the tube is where the other fluid goes. And the plate and frame has opposite, like hot cold plates that are all stacked next to each other, and you can change how many plates you want. So as far as flow arrangements for tubular heat exchangers, you could class shell and tube as tubular, but most people think of just like a concentric tube whenever they talk about tubular heat exchangers. They have three different flow types: parallel, counter, and cross. Counter is your most efficient because you get the largest delta T, but in reality, shell and tube heat exchangers have all three of these. You're trying to get the most turbulence to get the most heat transfer. So for a shell and tube heat exchanger, this is a super simple diagram of one. where you can see the hot fluid gets lighter in color because it's losing heat, and the cold fluid gets lighter in color because it's gaining heat. The baffles shown there are inserted not only to support the physically support the tubes, but also to aid in the turbulence of the warm fluid in this case, because that gives you a better heat transfer rate. And these types are probably the most common that you see in industry. They've been around for a long time and they have a lot of wide applications. You can change the number of tubes to increase your surface area, but because it's tubular flow, that means it's primarily laminar, unless you have like, a lot of them have like a U-bend on the end that increases your turbulence as well, but it's still primarily laminar inside of those tubes, which that makes your fouling worse because you have more chemical deposits on the inside of those tubes. These are very efficient, but they do require insulation because there is heat loss on them, but they aren't as efficient as plate and frame heat exchangers, which as you can see here, like I said, it's hot, cold, hot, cold. These are probably one of the most efficient types of heat exchangers. They're even less expensive and more physically compact. They have turbulent flow because there's no pipe flow, and the gaskets separate the hot and cold fluids. But the reason why these probably aren't as common is because they aren't really ideal for high temperature cases, which a lot of heat exchangers are used for. The reason they aren't ideal is because of those gaskets, like I mentioned. As soon as you increase the temperature above a certain point, it like dramatically increases how often you have to replace them. So as far as selecting between those two types, you need to look at your operating temperature, your fluid properties, and your cost. If you have a really high operating temperature, probably want to go with shell and tube. If you have a really like nasty fluid, you might want to go with plate and frame. But it really boils down to the cost, and like it's kind of a balancing act of what you're looking at. How often are you going to have to do maintenance on it? How much real estate do you have? How much money do you have to spend on installing a new heat exchanger? And then lastly, for applications of heat exchangers, every air conditioning unit is a heat exchanger. It's cooling air. Lube oil cooling is a really common one in plants. Any piece of machinery that's heating up and needs to be lubricated usually has a lube oil cooling system, and that system has a heat exchanger. Also, water cooling. Water is also probably one of the most common fluids in any plant, and heat exchangers are needed to cool those as well. Those are my references. Any questions? Yes.
I was just curious why you chose those two. Are those most like widely used in the industry?
There's so shell and tube has its own configurations, so there's a lot of different types of shell and tube. There's also like spiral ones, but these are the two that are like kind of most simple.
Okay.
Yeah.
Cool.
Okay, now could you just give me a clap? The condenser at the back of the refrigerator.
At the back of the what?
Yeah, of the refrigerator. Yeah. It's also an heat exchanger, right?
Mm-hmm.
So what does it exchange heat with?
The back of a refrigerant and like water. I don't know. Make ice in your freezer. Or air.
So what is it actually? It's air, right? Because it's correct, it's air. It exchanges heat with air. And do you know why they are actually fins? Like if you should look at your refrigerator, that's the condenser part. We have like fins. Like what does those fins help to do? Like
It dissipates the heat.
So I'm going to tell them in my presentation.
My 6-minute talk is all about heat exchangers.
why?
Well,
Okay.
I mean, the fins are used to like, it adds more surface area, so you
Yeah.
get a greater heat transfer.
Good answer.
Why is everybody running to eat